This video will be covering Section 3.3, Summaries for Skewed Distributions. Since the mean is not resistant to outliers, it is not the best measure of center to use in a skewed distribution. So today we'll be looking at measures of summary measures for skewed distributions, both center and spread. So let's take a look at the distribution of salaries in millions of dollars for professional baseball players in 2010. The mean salary in 2010 was 3.2 million and is marked by the triangle on the horizontal axis. So remember that the mean really is the balancing point of the distribution, and the mean follows the tail. So it's pulled by outliers, and so it's pulled in this direction. And not a very good summary statistic when you have a skewed distribution. So almost 70% of the players actually made less than that mean salary. A more accurate typical, we could say, salary for these players is located closer to the middle of the distribution, and a salary that had roughly 50% of the salaries above and below it. So where do we think the middle of the distribution lies? Probably somewhere around this vicinity, maybe near the 1 million mark. And the measure of center that is more useful with skewed distributions, so we'd always have to look at what our data looks like to know whether it's skewed or symmetric, is the median. The median is a numerical summary that measures the center of a distribution, similar to the mean, in that way, and it gives us a typical value for a data set. So the median is a measure of center, and what it does is cut your distribution roughly in half, with 50% of the distribution above it, 50% below it, and it's the one we choose when we have a skewed distribution. So the following contains the incomes of 1,000 New York State residents drawn from a survey done by the U.S. government in 2011. The mean income was 42,101 and it's marked with our triangle here. So again, you can see that the mean is being pulled towards the tail. So estimate the percentage of residents that earn more than the mean income. And so we want to know what percent earns more than the mean. And if we look at, maybe we look at the percentage that earn less than the mean, it looks like out of 1,000, maybe 650 are less. So 65% would be less than the mean, leaving 35% to earn more than the mean. So now looking below at number 5 here, the following histogram shows the same distribution as above, but has a vertical line indicating the median income. Notice that this line, which is 25,200, cuts the area of the histogram in half. So now we have a line that's showing us where 50% of the incomes are less and 50% are more. And this is a better method of summarizing center when dealing with a skewed distribution. So if you have data, you want to look at your distribution, or at least you want to think about what shape do you expect the distribution to be. So income, housing prices, salaries at a company, those all tend to have skewed distributions, and therefore the median is a better measure of center. So now, how do we find the median? We don't want to do it just by guessing on the histogram. The steps are to, 1, sort the data from smallest to largest. And if the data contains an odd number of observations, so if n is odd, then the median is just the middle value. If n is even, we want to average the two middle values to come up with the median. And this formula, n plus 1 over 2, can be very helpful to find the position of the median. It's not the median itself, but rather the position of the median. So we'll look at that formula down below as we calculate the median for some of these small data sets. So here in this first data set, we have n is equal to 7. Okay, so that's odd, which means that our median is going to be our middle value. And we can just look at the data set because it's so small and determine which is our middle value. We have 3 above and 3 below, making 8 our median. So if we use this formula, n plus 1 over 2, to find the position of the median, let's take a look what happens. N is equal to 7 plus 1 over 2. So our position of our median is at the 4th position. So we'd have 1, 2, 3, and 4, which tells us that the 8 is the median of the data set. The next data set, n equals 8. So when you have an even number of data points, you're going to take the average of the two middle data points. So in this case, our median would be the average of 8 and 10, which is equal to 9. If you use the position formula and you have n equals 8, you'd have 8 plus 1 divided by 2 gives you 4.5. Now this is the position of the median, meaning that if we count over, we can count over 1, 2, 3, 4, and it tells us it's 4.5, which is going to be the average of the two middle numbers. All right, now let's look at the median of the next data set. N equals 8 again. So again, we're looking at the median being the average of the two middle data points. We have 3 data points that are below that. So our average here would be 9.5, and actually I should say we have 4 data points that are below this. Okay, sorry, I have a mistake. The average is 9. Okay, there we go. And 4 data points above. Notice the last data point in this data set here. We have 16,000. So if we had calculated the mean of this data set, our mean would have shifted. It would have been pulled way up. But the median, notice, doesn't have any change from the data set above, even though we have this extreme outlier in this data set. And so we can notice that the median is resistant to outliers. In other words, an outlier doesn't change the median. And that is why it also is another reason why it is good for data that is skewed. Okay, the following dot plot shows the percentage of fat for each of the 10 types of sliced ham at a grocery store. This is an example from your textbook. Find the median for this data set. So we have n equals 10. So the position of the median will be 10 plus 1 over 2 is 5.5. So we're going to take the average of the 5th and 6th data point. So let's count over 1, 2, 3, 4, 5. So the fifth data point is 22 and the sixth is 25. So the median is equal to the average of 22 plus 25 divided by 2, which comes out to be 23.5. So based on our answers in this, the last couple examples, do we think that the median is resistant to outliers? And we noted it in example number 9 above, and then in 10 here, we're kind of looking at a skewed distribution. Yes, it is resistant to outliers. So this is why we use a median when we have a skewed distribution. Now let's take a closer look at how the mean and median are affected by outliers. This is a little bit of a review. Okay, so what we want to do is mark in which line is which. Okay, so you can see our data set here. And which line do you think is the mean and which is the median? So the mean is going to be pulled in the same direction as the tail of your data set. So this will be our mean. And the median is going to cut our data set in half. So if we take a look, we have 1, 2, 3, 4, 5 over here. And 1, 2, 3, 4, 5. This will be our median. The next dot plot shows a percentage of fat from 10 types of sliced ham, but the percentage of fat has been changed for the type of ham with the highest percent. How did this affect the location of the mean and the median? Well, the median didn't shift. It's still in the same location. So no change to our median. But what happened to our mean? Let me scroll down a little so we can see both. Notice that the mean was pulled in this direction because we have this new data point out here that's way out at 65%. And so that pulled the mean. So the mean was pulled toward outlier. If a resistant measure of center is better to use on skewed distribution, then what do we think about spread? Do you think standard deviation is resistant to potential outliers? So if we remember, our standard deviation worked closely with our mean. In fact, we used the mean in the standard deviation calculation. And so no, it would not be resistant to outliers. And so we're going to need to look at a measure of spread that is resistant. Okay, so here is an output from Fathom, that is a statistical software. The first line here is showing us our mean. Then our next line is the median. And then we have our standard deviation. So the left includes Tom Brady. So this is the ages of the New England Patriots, and the left includes Tom Brady as if he were right now in 2015 season. Well, the output on the right shows what happens if he still played when he was 60. So you can see we'd have this skewed distribution because now we'd be having a player with an age of 60. And you can see that the mean changed, the standard deviation changed, but the median stayed the same. So that's another look at how the standard deviation is not resistant. So it's not a resistant measure of spread. Since the standard deviation is not resistant to potential outliers and not good for skewed distributions, we need a better method of summarizing skew distribution when we want to talk about spread. And this is called the interquartile range, often seen as the IQR. The IQR is a numerical summary that measures spread of the distribution by finding the middle 50% of the data. How do we calculate the IQR? Here are the following steps to calculate it by hand. The first step will be to find the median of the data set. And this value will be called, not only is it called your median, it's also the second quartile. In other words, 50% of the data is less than your median. Once we've found the median, we are going to find another median of just the lower half of the data. This will be our first quartile. So we'll have Q1, where 25% of the data is less than it. We've found Q2, or the median, so 50% of the data is less than Q2. And then third, we will find the upper median of the upper half of the data set. This will be your Q3, okay? And then 75% of the data will be less than your Q3. But that's 50% less than Q2 because that is your median. Okay, then the final step is that we want to find the, we're going to subtract the first quartile from the third quartile, and this is going to give us the difference here that will be the spread of the middle 50% of your data. So there are more than one way to calculate the IQR. The first example here I'm going to do will be the way we do it by hand, okay? But occasionally some of the computer programs do something slightly different, so we're going to look at what happens with technology when they calculate the IQR. So step one is to find our median. Our data set is n equals 9, so we have 9 data points, meaning that our median will be our middle data point. So our median, which is equal to Q2, is 24. Next, we need to find the median of the lower data set. So this is our lower data set here. We're not using the median in this calculation. And so that will be the average of the second and third data points. So our Q1 will equal 15. And then we do the same thing for the upper half of our data points. Again, not using the median in the calculation. We're going to find the average of our upper data set, which is Q3, is going to be equal to 47.5. And then finally, the last step, your IQR is equal to Q3 minus Q1. And in our case, 47.5 minus 15, which is equal to 32.5. Okay, now StatCrunch uses this method for finding the quartiles. Which is slightly different, which may change your IQR. So they find the median the same way. So our median is still 24. But now when they go to find the median of the lower data set, they include the original median in the calculation. And so for StatCrunch, Q1 will equal 20. And then they include the median in the upper. So now our Q3 will equal 45. And so your IQR will equal 45 minus 20. So it's a slightly different calculation. Remember that we've also talked about the range, which is the max minus the min. And so in this case, that would be equal to 60 minus 0, which is equal to 60. And we can see that the the range is not resistant to outliers since we are actually using the two end data points. So find the range and IQR for the following data set. So your range, which is a nice quick and simple calculation, will be 14 minus 2, which is equal to 12. Our IQR, we need to go through all the steps. First, finding our median. This is our Q2. Now we are going to find Q1, which is the middle of the bottom data set, and then Q3, which is going to be the middle value of the upper half. So our IQR is equal to Q3 minus Q1, which equals, okay, let's do it again for the next data set. Now our range will be 16 minus 2 equals 14. Our median is going to be the average of our middle data points because our new data set has 8, which is even. So our median is 9. When we have an odd and we take the average, now since the median isn't actually one of our data points, we're going to use all of this in our lower data set to find our Q1 is going to be equal to 5, the average of these two data points, and Q3 is equal to 13, the average there. So IQR equals 13 minus 5, which equals 8. Okay, we're going to do one more data set together. The range, okay, our max is 16,000 minus 2 is going to be equal to 15,998. That's quite the difference, and we've been seeing. And our IQR is equal to, we're going to again have 9 be our median. 5 Q1 equals 5. And Q3, so there's no change here, equals 13. So our IQR will be 13 minus 5, which equals to 8. So this data set really shows that the IQR is resistant to outliers and very good measure of spread when you're talking about a skew distribution. So how does the IQR differ from the range? And the IQR, we're really talking about our middle 50%. How spread out is the middle 50%, where the range is only looking at max and min. The quartiles cut the distribution into 4 parts or quarters, with roughly 25% of the data in each quarter. The dot plot below shows the distribution of weights for a class of introductory statistics students. The vertical line represents their quartiles. Use this graph to estimate the median, quartile 2, quartile 1, quartile 3, and the IQR. So each of these lines represents our quartiles. And we can use the dot plot to figure out what the value is. It looks like Q1 would be equal to about 121. Maybe Q2 is equal to 135. And Q3 looks like it's equal to 160. So now using this information, we can calculate our IQR, which is Q3 minus Q1, which is 160 minus 121, which equals 139. So this is talking about the spread of the middle 50% of the data. So this right here, we're looking at the spread of this area, of this data right here that's in the middle 50%.